In this video, we're going to talk about integration by partial fractions. So the motivating question here will be an integral like this, x plus 5 over x squared plus x minus 2. You might look at it and attempt integration by substitution, where possibly you let the bottom equal u. If the bottom equals u, though, du will not look like x plus 5. The derivative of x squared plus x minus 2 just won't quite match up well with x plus 5. So substitution is actually not going to work. The technique of integration by partial fractions, what we're going to do is break the fraction x plus 5 over stuff into two separate fractions. And first I'm going to convince you that that's okay, that we can do that. And then afterwards we'll apply it. We'll see that this integral turns into something a lot more simple. So the goal with partial fractions is first to factor the denominator. And here it will be x plus 2 times x minus 1. Now the basic claim of the partial fractions is that we can take that fraction and separate it into two parts. Now the two parts are going to be something over x plus 2 plus something else over x minus 1. And our job is to figure out what over x plus 2 plus something else over x plus 1 is equivalent to that fraction. We're going to call the numerator a. Usually in most textbooks you'll see this is using a capital letter. And we'll call the numerator here b. So by the end of this, we'll find a and b. And then we'll take our a and b and we'll split this integral into two separate integrals. So to do that, what we're going to do is multiply by x plus 1 in the numerator and, x minus 1 in the numerator and denominator. So we'll multiply that one by x minus 1. And this one by x plus 2. Thus making the denominators common. So that'll become ax minus a plus bx plus 2b, all of that over x plus 2, x minus 1. So hopefully you agree that this fraction has the same denominator as this fraction. And what the claim is that we can find some very special a and b values where the numerator will actually be x plus 5. So when you see x plus 5, I don't want you to think about x. I want you to think 1x plus 5 constants. So anything that has an x in the numerator, we can add those up and equate those to one total x value. So we have ax plus bx, so ax plus bx must equal 1x. This 1 comes from this one. The other two terms that are there, negative a plus 2b, those don't have x's on them, so they have to add to 5. So now that's negative a plus 2b, that adds to 5. And you may notice in this equation they all have x, and we're not interested in finding x. We're interested in the coefficients. So I'm just going to effectively divide those x's away. Now we have a system of equations in a and b. So actually if we add these two up, we'll get 0 a's, 3 b's, and that equals 6. Thus b equals 2. So we'll need that. And if we take b equals 2 and we substitute it back into this equation, you'll have something plus 2 is 1. So a will be negative 1. And you can check in this equation that it works. We'll have negative 1, negative 1, which is 1, plus 2 times 2 will give us 5. So now we found our a and b. What that means is, go back to the sort of the original idea, we could take our fraction and break it into two pieces. So that means this fraction that has 1x plus 5 over the factored terms is actually equal to negative 1 over x plus 2 plus positive 2 over x minus 1. So that's the integral negative 1 over x plus 2 plus 2 over x minus 1. So we took this fraction and we split it into two pieces. If you don't believe that this would be that this is actually the proper value, I encourage you to add those two up. So I'm just going to check it over here. We'll multiply the top and bottom of this by, multiply the top and bottom of this by x minus 1, so it'll be negative 1 x minus 1. Top and bottom of this, get an x plus 2, that's 2 x plus 2's, and our denominator is common now. That'll be a negative 1x plus 2 more x's, that's x. And now negative 1 times negative 1 is positive 1 plus 2 times 2. There's our x plus 5 over our factored terms. So what I did on this rightmost portion here is just confirm that the 2 and the negative 1 do in fact do the trick. So the point of doing this is that now we can take each of these and integrate them separately. You may notice that these are natural log integrals. So this will be, well, this one's maybe a little easier to see. This one's just the natural log of the absolute value of x minus 1 plus a constant. And the 2 is there because it's in the numerator. This guy has a negative 1 times the natural log of the absolute value of x minus 2. Just recall that I put absolute values here because the natural log won't take a negative argument. So this turns out to be the integral of the original, and you can see how u substitution would not have led us anywhere near this. To recap, the general technique is to factor the denominator, and once you have a factoring, you try to figure out what special separate fractions can yield the same 1x and positive 5. And those are the two key numbers. We have to do all of this work here to find what the numerators would be that would yield a 1x and 5 constants. And then you'll get an integral such as this one. Very often these are going to result in natural logarithms. In the end, I added the constant, of course, as a constant of integration. If this was a definite integral with limits on the top and bottom here, all we would do is we would evaluate this without the plus c. We would evaluate this from bottom to top and subtract accordingly. So this is the technique for integration by partial fractions.